Hello and welcome to the 7th in our series of webinars teaching you how to use LabVIEW for the FTC competition. On behalf of myself, Ben Zimmer from Enable Training and Consulting, my colleague Greg Sullivan,
Hi,
and our friends at National Instruments, I'd like to welcome you. In the previous webinar, we discussed an interesting programming architecture called state machines. We discussed how to create state diagrams to represent them, and we took a tour of an example code which used a state machine to implement some autonomous robot code. As a quick review, the basic purpose of state machines is to break up a robot action into a series of modes or states, and to make decisions in each state based on what action is to be performed next, based on inputs and data available in the current state. In general, state changes are made based on values input by sensors, but also information collected throughout the program can be used to make those decisions. State machines are created by placing a case structure within a while loop, also implementing a shift register within that while loop to remember the state information. Strings can be used to define that state information and used as the input to the case selector in the case structure. One of the benefits of using strings is that it makes it easy to distinguish between states because they can be given descriptive and human-readable names. Now, state diagrams are a way to represent the state machine. They show program flow using arrows for a transition between states and circles to represent the states themselves. And transition arrows themselves are often labeled with an action that happens during the transition or an input which triggers that transition. So as an example, we see this state diagram here. It's this type of pseudocode to visualize the steps. So here we see we're going from the start state to the first state to the second state and finally to stop. Now naturally that's a pretty trivial and straightforward example, but we saw the benefit of using the state machine and the state diagrams in the code that we investigated last week. In that webinar, we wrote a program that once it detected an object moved forward for a second, then backwards for a second, and then continued checking for an object. One of the most important steps in writing code is envisioning the state diagram. And we discussed in several steps the idea that we started off the program by going to an idle state. And then the idle state, when an object was detected, would move into the forward state. And then the forward state, after a second, would move into the backward state. Finally, after a second, the backward state would then transition into the idle state. And the last piece of this programming puzzle was that when a touch sensor was pressed in any one of the states, the whole program would go to a stop. So what we're going to do in this week's webinar is to take the step a little bit further, to describe a more sophisticated state machine and one that's also more responsive. Because one of the problems we saw in this particular implementation was that it always took at least a second for the robot to respond. So in this week's webinar, we're going to discuss some tools that we need in order to implement a more sophisticated state machine. The first is a nested case structure. We're going to talk a little bit about reusable code, and then we're going to dive into a slightly more sophisticated problem and solve that problem. Nested case structures are created by placing one case structure within another. And this is a very common programming technique that allows us to handle when sensor cases are often combined together. So when we have multiple components such as sensors and we need to do a certain action when something is true but something else is false, you can envision how using multiple case structures allows us to write that code. Reusable code is a concept that's really important to consider and one of those which state machines in general do a really good job of using. The idea is that you reduce the time it takes you to program, reduce the size of your program, and of course, because the code is simpler and smaller, your code is also easier to debug. So the idea that we can reuse states to perform the same actions is one which we're going to investigate in this solution as well. So the goal of this week's webinar problem is to create a program that's going to search for an object. And when it detects that object, it'll start moving forward. This is similar to what we had at the beginning of the problem from last week. However, now, from the forward state, if it detects another object, it's going to start moving backwards. Or if the touch sensor is pressed, the motors are going to stop immediately and then wait for another object to be pressed. So already this is a different, although similar example to last week's. While moving backwards, if an object is detected, it's going to start moving forwards again. Or if the touch sensor is pressed, the motors are going to stop and it'll wait for another. So this is a nice big long paragraph, and it's a little bit hard to parse when you read it at first. So the first approach we should always take when we're going to do this kind of programming is to create our state diagram. So let's break the problem apart and come up with our state diagram. Well, the first thing we need is something to sit and wait for the sonar sensor to detect an object. So our first transition and our first state is going to be to go from start to idle. Step number 2. So when an object is detected, the motors will be set to start. So when the sonar detector hears a sound and therefore it senses an object, we're going to go from the idle case to start motor forward. Now this state is a little bit different than what we implemented last week. Start motor forward is a kind of state that we can often describe as transitory. It performs an action and then immediately moves on to another state. Let's see what that looks like. So after the motors start, we then transition into a moving forward state. So we'll see when we implement this the value of having the motors started separately from the actual state where we're waiting for something else to happen. So notice that there's no words on the transition arrow from the start motor forward. It just automatically and immediately transitions from start motor forward to moving forward. But from the moving forward state, this is where we have two transitions. One, if there's a touch sensor pressed, it's going to go to the stop state. And two, if the sonar detects something, it's going to start motor backward. Then finally, we complete the diagram by finishing off the states and the transitions from motor backward. So after starting motor backward, it's the same thing. We have an immediate transition into moving backwards. And then we have two possible paths: on the touch sensor to stop, or if another object is detected by the ultrasonic detector, moving back to start motor forward. So take a moment now and follow this path through for yourself, and you'll see it's a little bit more complicated than last week, but really offers most of the same functionality, but as we'll see is much more responsive.